When the torque acting on a body is 0, then which one of the following quantity remain constantes? We know from the rotational forms of Newton's second law, torque is always equal to a change in angular momentum with respect to time. So from this equation we can see that when torque is equal to 0, that is when torque is equal to 0, the change in angular momentum divided by time, or with respect to time, is immediately 0. Then we can say that the change in angular momentum of the body is equal to 0. Change in angular momentum is 0 means the angular momentum remain constant. This means that the final angular momentum minus the initial angular momentum is 0. This implies that directly the final angular momentum is equal to the initial angular momentum. This is the conservation of angular momentum. When there is no external torque is acting on a rotating object, that means when the sum of all the torque acting on a rotating body is 0, the angular momentum of that body will remain constant. So according to the equation, if the torque acting on a system is 0, then the angular momentum of the body remain constant. So the correct answer is on alternative C. The hoop of mass m and radius r is sitting on an inclined plane h. Then it rolls down and reaches the bottom of the inclined plane. So at the point where it reaches the bottom of the plane, what will be the angular momentum of this hoop? So we know that when the hoop rolls down, it's performed two types of motion. The first one is its center of mass is moving with the velocity v, and at the same time the hoop is rolling with an angular velocity omega. So it has two kinds of kinetic energy, that is translational kinetic energy due to the velocity of the center of mass v, and the angular kinetic energy due to the rotation. So then from the conservation of energy, the total energy of the hoop when it is sitting or when it is at the height h on the inclined plane is given by mass times gravity times the height, and after it rolls down, it has a two kinetic energy. One is translational kinetic energy, a half of mass times velocity square, and a half of I omega square, moment of inertia, and angular velocity square. So we know that the moment of inertia of the hoop is given by mass times r square, and also we know that the linear velocity of the object is, or the linear velocity of the rolling object is given by v is r times omega, then v square is r square times omega square. Then I substitute the place of moment of inertia and velocity square in the given equation. So this gives me directly a half of m r square omega square plus a half of m r square omega square is equals to mgh. So this means that if I directly add these numbers together, mr square omega square is equals to mgh. So then we can cancel mass from both sides, and we have left with gh is equals to r square times omega square. So then we can find the angular velocity, which says that angular velocity square is gh divided by r square, and then omega is under radical of gh over r square. So this can be simplified as omega is 1 over r times the radical gh. Then we know that the angular momentum of any object is given by its moment of inertia times the angular velocity. So the moment of inertia of the hoop is already known. It is m times r square times the angular velocity is, we have calculated right now, which is 1 over r radical g times h. So from this equation, 1r cancel with the others, and we have left with m times r radical gh. So this is the final answer. So the correct answer is on alternative A. A body is rotated with a uniform speed in a circle of radius 1 meter. What is the centripetal acceleration of this object is in meter per second if it is complete 12 rotation in 3 seconds? So to find the centripetal acceleration, we have to find the angular velocity of omega. Simply, the centripetal acceleration of the object is simply the tangential velocity squared divided by r. Since the velocity or the linear velocity and omega are related by v is equals to r omega, then we can write this is r times omega square if we substitute the values of v. So then the centripetal acceleration is r times omega square. But omega is given by the angular displacement divided by time. Angular displacement of the object is 12 revolution, which is 12 times 2 pi radian. So to convert the revolution in radian, multiply it by 2 times pi and divided by 3 seconds. So this is directly gives me that this by 3 is 4 and this by 3 is 1. Then 8 pi rad per second is the angular velocity of this rotating object. Then the centripetal acceleration is AC is equals to r times omega square, since the r is 1 meter, and multiplied by 8 pi rad per second the whole square. So this is equals to directly 1 meter, 8 square is 64 times pi square rad square per second square. Rad is dimensionless quantity, so we can cancel from this, and also I multiply the number, so 64 pi square, 1 meter is left, divided by the second square. That means centripetal acceleration of this object is 64 pi square meter per second square. So the correct answer is on alternative B. The position of the swinging door is theta of t is 5 plus 10t plus 2t square. Then what is the angular velocity and angular acceleration of this door at time t is equal to 3 seconds? So to solve this equation directly we use the derivative. So the angular velocity at any time is the first derivative of the position function, that is d by dt of 5 plus 10t plus 2t square. This is directly gives us that derivative of 5 is 0 and derivative of 10t with respect to time is 10 plus derivative of 2t square is 4 times t. So this is omega at any time t, which is 10 plus 4t. When t is equal to 3 seconds, omega of 3 seconds is equals to 10 plus 4 times 3, which is equals to 10 plus 12, that is 22 rad per second. So this is the angular velocity at 3 seconds. Then the acceleration, angular acceleration at any time t is given by the first derivative of the velocity function, or it is the second derivative of the position function. So this is d by dt of 10 plus 4t, since velocity at any time is 10 plus 4t. So we can write this that derivative of 10 with respect to time is 0 and derivative of 40 with respect to time is 4. So alpha is not dependent on time. This means the object is moving with a uniform acceleration. So alpha is independent of the time. So the velocity and the acceleration directly given by 22 rad per second, 4 rad per second square. That is, the correct answer is on alternative A. The question says that which one of the following statement is not true? Then the not true statement is alternative A. Says the magnitude of average angular velocity is directly proportional to the angular displacement during a given time. So that means the magnitude of angular velocity at any given time is given by the change in angular with respect to time, or simply we can say it is theta over t. So the magnitude of angular velocity is directly proportional to the angular displacement theta. That means omega and theta are directly proportional to each other. So this statement is directly true. Alternative B says that average angular velocity and instantaneous angular velocity are the same for a uniform angular motion. So this means that the average angular velocity is equals to the total angular displacement divided by the total time taken, and the instantaneous angular velocity omega instant is the limit of the change in theta, that is the change in angular displacement with respect to time, as the change in t is approaches to 0. So if the motion is uniform, omega is not changing with time. That means if omega is not changing with time, that means if motion is constant, uniform, omega is constant. This means that the average angular velocity is equals to the instantaneous angular velocity. So this is true always for a uniform angular motion. So it is true. Alternative B is still true. When we come to alternative C, which says the direction of average angular velocity is determined by the right hand rule. This means that if any object is moving along with some angular velocity omega, then the object is moving with some angular velocity, is moving. If this is the tangential velocity of the object, is the direction of angular velocity is always at right angle or perpendicular to the plane of rotation. That means omega is determined by the right hand rule. So this is still true. When we come to alternative D, it says that the direction of average angular velocity is parallel to a tangent line along the trajectory of the object. So if the object is rotating with some tangential velocity v, the direction of angular velocity is determined by the right hand rule from alternative C. We have seen that. And the direction of tangential velocity is tangent to the trajectory of the object. So the velocity which is tangent to the trajectory of the rotation is the tangential velocity v. It's not the angular velocity. So the only not true statement among the given alternative is on alternative D. So if the disk is rolling without slipping and the center of the disk is moving with a velocity v, then what is the velocity of the point at the top rim of this disk? So we know that from the rotational motion, the center of mass, or the position of center of mass of the disk is at the center of the disk, and that is moving with the velocity v. Then we directly know that the point at the bottom of the circle is at the velocity 0, and the point at the top rim of the disk is moving with a velocity of twice of the velocity of the centers, 2v, and the center is moving with v and the bottom is moving with a velocity 0. That means it seems momentarily at rest, where the center of the disk is moving with the velocity v. So the correct answer is the top of, or the upper point of the disk has a translational velocity of 2v, and the correct answer is on alternative C. So the angular momentum of a particle is A, independent of the specific origins of the coordinates. So this is completely wrong. That means the angular momentum of the object is dependent on the distance from the axis of rotation. That means if we assume the axis of rotation is at the center of these objects, maybe at the center of mass of the objects. So the angular momentum is dependent of the specific position at some origins. Alternative B says that the angular momentum is 0 when position and the momentum vectors are parallel. That means momentum vector and the position vectors are parallel, means the angle between r and PR is directly 0 degree. So the angular momentum of the object is r times p times sine of theta, which is immediately 0, because sine of 0 is 0, means the angular momentum is also 0. So in this case we can say that the perpendicular distance from axis of rotation and the linear momentums are parallel with each other. So this statement is true. Alternative C says angular momentum is 0 when it is position and momentum vectors are perpendicular. Momentum and the position vectors are perpendicular to each other. Theta between them is 90 degree. This means that the angular momentum of the object is the magnitude of the position vector or the distance from axis of rotation times the magnitude of linear momentum, the sine of 90 degree. Since sine of 90 degree is 1, then angular momentum has a maximum value if the position vectors and the momentum vectors are perpendicular to each other. So it is not 0. And when we come to choice D, not 0 for non-zero position and momentum vectors. That means L is different from 0 if R is different from 0 and P is different from 0. So this is not always true. That means the angular momentum is different from 0 if the position vector and momentum vectors are different from 0, only if R and P are not collinear. If the position vector and the momentum vectors are collinear with each other, either parallel or opposite, the linear momentum is immediately 0, even if their magnitudes are different from 0. So this statement is not always true. So the correct answer, for which always true, is on alternative B. Two disks with moment of inertia I1 and I2 are initially rotating with angular velocity omega 1 and omega 2 respectively. Then, while they are rotating, the disks are brought together as a one. That means their axes are parallel with each other, passing through their center, and the two combined disks get the final angular velocity omega. Then if the disks are got this final velocity, what is the values of this final angular velocity omega? So to do this, we can use the conservation of angular momentum. That means the angular momentum before contact and after contact are equal. So we have two systems, I1 omega 1 plus I2 omega 2 is equals to I1 omega final 1 plus I2 omega final 2. But we can say that omega final 1 is equals to omega final 2, which is equals to omega. That means the systems are combined as one and rotate together, or the disks are combined and rotates as a one disk. So they got some combined velocity omega. Then from the equations, I1 omega 1 plus I2 omega 2 is equals to I1 plus I2 times omega, the combined velocity omega. So the combined velocity omega is directly I1 omega 1 plus I2 omega 2. This is I2 divided by I1 plus I2. So this is the final answer of the velocity of combined disks. So the correct answer is on alternative B. wheel starts from rest and reaches a velocity of 12 rad per second in a time of 3 seconds. Then what is the angular acceleration of this wheel, and while it is accelerating, how much angle it rotates, or the theta of this wheel is how much? So to do this, I have to use, this is an example of uniformly accelerated angular motion. So we have 5 equations to solve this equation. So directly we have initial velocity, final velocity, time, and the angular acceleration is required, and also the angular displacement is required respectively. This one is the first one, this one is the second one. So for a moment, this just stop, don't consider theta, and we have 4 quantity, omega naught, omega t, and alpha, and the equation which relates these 4 quantity is the first equation, which says that omega is equals to omega naught plus alpha times t. So alpha is omega minus omega naught divided by t. So this is directly equal to 12 rad per second minus 0 divided by 3 seconds, which is directly equal to 4 rad per second square. So this is the acceleration. And then the displacement can be calculated, or the angular displacement can be calculated from any other equation which includes theta. So from the second equation, theta can be a half of omega plus omega naught times t. Since this is 0, directly we have a half of 12 rad per second times 3 seconds. So this by 2 is 6 rad per second times 3 seconds. Second cancel by second, and 6 times 3 is equal to 18 radian. So the correct answer among the given alternative is, which has this combination 4,8, not 8,4. Don't be confused here, because the angular acceleration is required first and the displacement is the second value. So the correct answer which has this combination is on alternative A. Which one of the following object has a large moment of inertia? Large moment of inertia if all of them have the mass m and the radius r. A solid disk, so we know that a disk of radius r and mass m, when it's rotating about the center of mass, the moment of inertia of the disk is given by a half of mass times r square. Solid sphere with a solid sphere of radius r and mass m has a moment of inertia of, which is equals to 2 over 5 mr square, 2 over 5 mr square, and a solid cylinder of mass m and radius r has a moment of inertia of 1 over 2 m times r square, and a circular loop, or simply a hoop, of radius r and the mass m has a moment of inertia of mr square. So when we compare all these values, the largest value is on choice C, which is the circular loop of mass m and radius r, which has a moment of inertia mr square. So the correct answer is on alternative C. The largest moment of inertia among the given alternative is that of the circular loop